Okay, so this is the video, the prep video for section 2.2, where we're going to keep talking about limits, but we're also going to include limits that either are going to infinity or as x goes to infinity. So a few things that we need to remember from last time. We need to remember that we have one-sided limits. We remember that would either be from the left or from the right, and we write them this way. The limit as x approaches a particular value from the negative side, that'd be a left-sided limit, or from the positive side, that would obviously be a right-sided limit. And then we have two-sided limits. Two-sided limits exist if the right limit and the left limit match. So two-sided limits exist if the right limit equals the left limit. And then we introduced the notation D and E for does not exist. If the right and left limits do not match, or are not the same, then the two-sided limit does not exist. We need to add a little bit something here, though, about infinity, because technically infinity does not exist, but we are actually going to use infinity as an answer in some cases, because we'll use infinity to indicate behavior, not a value. So clearly, infinity, the value does not exist in the sense that I can't write it down. I don't know what it is. But infinity, the behavior, I know what that is. So we will use that. Okay, so let's start with rational functions. So we're going to start with this function, f of x equals 1 over x. And again, this is a function that we should know what it looks like. If you don't, you can always use Desmos or your calculator, but really this is one that we should know. And why do we know that it looks like that? When the denominator is equal to 0, we have a vertical asymptote. There it is. And we know that when x gets very large, coming way out here, 1 divided by any extremely large number is an extremely small number, so we're heading towards 0 that way. Okay, so let's look at some limits. Let's look at the left-sided limit. And we'll also look at the right-sided limit. And then we'll think about the two-sided limit. I know, lots of writing. Just the way it is with limits. Okay, so from the left, we're looking at x is at 0, so this is the place that's what we're aiming towards, as we're considering the behavior of the function. So we're tracing along this function, and we're following the function heading towards this dotted x line. So where's the function going? It's going to negative infinity. So again, negative infinity doesn't exist, but it's a behavior, so we're going to say that this is, and if you want to, you can use an arrow, headed towards negative infinity. Okay, what's it doing on the right side? So again, we're following the function, heading towards this dotted line, following the function, and clearly that one is going to positive infinity. So, does the two-sided limit exist? Well, on the one side it's heading to negative infinity, on the other side it's heading to positive infinity, so no, this limit does not exist. Okay. But one thing that we can notice is a pattern here. When x approaches a finite number and the y value heads off to infinity, that really is the definition of a vertical asymptote. So let's just come over here and include that. So we know we have a vertical asymptote that is defined in terms of limits when we say that the limit as x approaches any particular finite value. So we're not talking about x squared, which heads off into infinity as x gets big. We're not talking about that. But if it starts screaming off to infinity as you approach a finite number, then that would be either plus or minus infinity. That is the definition of a vertical asymptote. sorry, I didn't want to stop the video and start over. Okay, so let's look at another function. So we're going to ask some of the same questions. So I'm going to leave some of this up, just so I don't have to rewrite it. Okay, so let's look at this function. Get the pen open. 1 over x plus 2 quantity squared. So again, another rational function. What do we know? We know that x equals -2 will be a vertical asymptote, so we know we're over here. And what else do we know? We know that because it's a squared term in the denominator, that denominator can never be negative. It can get very large or very small, but never negative. And so this looks like this. And that's a shape that's one of those shapes you may want to commit to memory. This, with the asymptote at 0, is 1 over x squared. Okay, so we're going to ask the same set of questions. Left-sided, right-sided, and two-sided limit as x approaches -2 from the left side, the negative side, and -2 from the positive side, and then the two-sided limit. Okay, so from the negative side, again, here's our dotted line that we're interested in. So we're aiming for the dotted line. We're following the curve, clearly going off to positive infinity. And from the right side, it's actually doing the same thing, going off to positive infinity. There is no point. We should be clear that f of -2 does not exist. There is no point there. From both directions, it's going to infinity. So because the limit from both sides, from both right and left sides, are going to the same place, this limit actually does exist. And again, if you guys would prefer to write, maybe it makes a little bit more sense intuitively to use arrows instead of equal signs. So in this case, the left and right side limits are both going to a positive infinity. They could, in another example, both go to negative infinity. But if they're going to in the same direction, then the two-sided limit exists. Okay, so one last reminder, which is that not everywhere that a denominator is equal to 0 is a vertical asymptote. So let's go back and look at that just as an example. Okay, so one last one. So let's look at f of x equals x squared plus x minus 2 all over x squared minus 1. So the first thing we always need to do when we're looking at rational functions is to factor top and bottom. Anywhere that factors cancel, we're going to have a hole in the graph, and then that will leave us the remaining simple graph that we can graph from there. So to be clear, these x squareds do not cancel. And the 2 and the 1 cannot cancel. You can only cancel multiplied terms, and I see plus and minus signs. So these are not multiplied terms yet. So let's go ahead and factor. So x plus 2, x minus 1 over x plus 1, x minus 1. Now we have multiplied factors. These factors cancel, telling us that we have a hole in the graph at x equals 1. That means that this is the remaining graph that will show the shape of the graph. Okay, so we need to think about what that's going to look like. Again, the point, did I cancel correctly? Let me just make sure that I wrote the same as the notes that I wrote. Okay, so the thing to remember then is that this class is not right now not about spending a lot of time graphing. So I don't mind if you use a calculator or Desmos, which is great, to graph this. In fact, I'm going to use Desmos just to double check what I think I already know. Okay, so what do we know? We know that we have a vertical asymptote. I guess I wrote here. We have a vertical asymptote at -1. We know that the ratio of the two, they're going to, as x gets very large, basically the same large number over the same large number, the ratio is going to be 1. So horizontal asymptote at 1. If we put in x equals -2, we find that that will give us 0. So x equals -2 and 0. That's our x-intercept. And if we put in x equals 0, we'll get 2 over 1, so that's our y-intercept. So we've got some points. We know roughly that this thing is going to look, kind of that shape. So this is really enough to graph, and then if you wanted to check, you could with Desmos. So it looks like this and like this. Okay, so again, let's ask our questions. What is the limit as x approaches -1 from the negative side? The limit as x approaches -1 from the positive side, and then we'll talk about the two-sided limit. And I did forget to put in, I have a hole in the graph at x equals 1, so I need to make sure to indicate that. So we'll look at that one too. Let's do that. Let's look at the limit as x approaches 1. Okay, so again, if it helps, in the case of asymptotes, we have dotted lines, but if you didn't, go ahead and dot them in. I think that helps know where you're aiming x in terms of the x value. So here, as x approaches -1 from the negative side, we start on the curve, and we see the curve is going to -infinity. If we start from the right side, you see that it's climbing, positive infinity. Again, that follows the pattern, so from a limit point of view, we know that that's a vertical asymptote. We also know that because it's going in a different direction, the two-sided limit will not exist. Let's look at this one. The limit as x approaches 1, just as a little review. Now we're going to have our dotted line, our x value of interest is there. Again, not a vertical asymptote, just kind of to know where we're aiming. And now if we follow the curve, we get exactly to a value. The value when x is equal to 1, which is 3/2, 3/2. So this one is a number. It's just a hole in the graph. Okay, so that's it.